Okay. Benjamin, welcome to our group, and thank you very much for agreeing to give a talk in our seminar. And yeah, a bit of information about Benjamin. He received his PhD from EPFL, Laboratory for Cryptology in Switzerland, and currently Benjamin, he also was a postdoc in 2019 at the Centrum Wiskunde en Informatics in Amsterdam, in Netherlands. And since 2018, Benjamin has been a CNRS research scientist at the Institut de Bordeaux in France, where he is a member of the number theory team. And his interests revolve around various facets of cryptology, with a particular interest on cryptologic algorithm, which relate to number theory and algebraic geometry. Another aspect of his work relates to randomness and blockchain technology. And he recently has published a paper on this topic. It's called Verifiable delay functions. And today he's going to talk about this. Thank you, Benjamin.
Thank you. Thanks for the introduction. And thank you for inviting me to speak to this seminar. So indeed, I'm going to be talking about verifiable delay functions, starting with what exactly they are. They are some kind of cryptographic primitive that was introduced quite recently, around 2 years ago. They were first formally introduced by Bonnet, Bono, Boons, and Fish in 2018 as a function that requires time to evaluate. But once you've evaluated it, verifying the result is actually efficient. That's the verifiable part of verifiable delay functions. So what does it mean for a function to be slow to evaluate? We actually want it to take time, to take real wall clock time to evaluate it. So we don't just want a function that requires a lot of computing power to evaluate. We actually want it to require a lot of sequential operations. So sequentials that must be done in a computations that must be done in a sequence, so that we know for sure that it's going to take a long time, even for an adversary that might have a lot of parallel power accessible. So we want this function that takes a lot of time to evaluate. Yet, once you have the result, you can efficiently verify that it's correct. The syntactically, a verifiable delay function consists in 3 components: a setup procedure, which just produces public parameters that are to be used to evaluate your VDF. Then an evaluation procedure, which is actually the procedure that takes time. It requires time, I'm going to say time t for the rest of the talk. Think about t to be something like 10 minutes. So this evaluation procedure takes as input an element x and computes an output y. In this sense, it's really a function. It takes an input and produces a unique output. And together with this output y, which takes time to evaluate, you can also produce some kind of proof phi that will allow the efficient verification of the correctness of this evaluation. That's for the third procedure, the verify procedure, which takes as input, well, the input x, the claimed output y, and the proof phi, and decides very efficiently whether y is indeed the correct output for input x. So this is just the syntax. We have security requirements for VDFs. The first one I already mentioned is the sequentiality. It's a property that says it does take time to evaluate, in the sense that any adversary that runs in time strictly less than t doesn't know anything about the output. If you have a parallel algorithm A that takes time strictly less than t, A is not able to distinguish the correct output of the VDF on input x from a uniformly random output. So this is the sequentiality, and we require a second property, which is the uniqueness. It essentially says that for a given input x, you have a unique correct output y. Formally, we say that if the verification procedure passes for twice the same x, so and 2 y's, y and y prime, so the verification for xy passes successfully and the verification for xy prime also passes successfully, then y must be equal to y prime. This property here would be perfect uniqueness. For a given x, there is a unique y. You might want some looser kind of uniqueness, for instance, computational uniqueness. That doesn't say that you actually have a unique Y for each X, but finding another possible Y would be computationally hard. So you can have a correct output Y, and maybe there exist other Ys that pass the verification, but they are computationally hard to find. So VDFs are a somewhat unusual kind of cryptographic primitive in that usually in cryptography, when you design a primitive, you require everything to go as fast as possible. You want everything to be very efficient so that everyone can communicate very fast. Here, you're trying to do the opposite. You're trying to design something that is slow on purpose and securely slow. You have a secure guarantee of slowness. So why would you want to do that? The initial motivation from that came from generating public random numbers. Public random numbers are pretty common. They've been around for a while. It's the kind of random numbers you find in national lotteries or in random draws for sporting events. It's just a number that you need to draw at random that has an impact for a lot of people. It's a completely public number, so it has nothing to do with the usual kind of randomness you see in cryptography, which is usually kept secret to generate secret keys. Here, no, it's a random number that's widely accessible. And all you want to do is convince the rest of the world that this number is indeed random. No one tried to cheat. No one tried to, or successfully tried to bias the outcome or predict the result ahead of time. So we have a lot of ad hoc methods to generate such random numbers. Typically for national lotteries, you would build a complex machine and you would film the process with balls flying around, and this would be sufficient to convince people that your outcome is indeed random. In a more technical setting, you would not be satisfied by these solutions. You would require some kind of cryptographic solution to generate random numbers. And cryptographers do have solutions to generate random numbers for a large number of participants. Here's a very classic solution. Suppose you have a group G of people, maybe you have 10 people, 1,000 people. They all want to agree on some random number. And these people, they don't trust each other. They want that the random number they agree on has some guarantee of being unbiased. No one tried to, no one could bias the outcome. So a classic way to do this, if you have a fixed group G of people, is to have everyone generate their own random bit string and keep it private for the moment. So it's the bit string RA here for each participant A. Then there is a first round of the protocol where everyone publishes a commitment to this random bit string. So they don't reveal the random bit string right away. They commit to it with a cryptographic commitment, which is hiding and binding, and they publish this commitment. So the commitment is hiding, meaning that from this commitment, no one learns anything about the random bit string. Then once everyone has broadcasted their commitment, the opening phase starts and everyone reveals their random bit string and they open the commitment. So everyone can know everyone else's random bit string, and they know that they couldn't change adaptively this random bit string between the moment they published the commitment and this second round. So at this stage, everyone knows everybody else's random bit string, and they compute the exclusive OR of all these bit strings, and that's the final random value. So this is a very classic protocol to generate randomness consensus about some randomness in a group of people. It's the commit then reveal protocol. And it works. We can actually work that it's, we can actually prove that it's pretty secure. As long as there is at least one honest participant, the outcome is guaranteed to be uniform and independent on any adversarial strategy. So if this is pretty secure, what's the problem there? The problem is that it doesn't really scale well for large groups of people because you have two rounds. You have a round where people publish his commitments, and then a second round where people open their commitments. And it's a problem for scale because if you have 1,000 people, you have a great risk that someone will drop between the two rounds, either maliciously or due to some technical problems. You may have participants that publish their commitment, but then disappear and never open the commitment. And then the protocol doesn't finish it because everyone is waiting for everybody else to open their commitment. So you could try to adapt a bit this protocol and say something like, okay, I'm going to wait 10 minutes. And if not everything is open after 10 minutes, I only consider the random bit strings that are opened at this point. But this opens the way for some manipulation from the adversary. So you don't want to change the protocol like this. And there's actually no easy fix to this protocol that would allow it to be so flexible that it works for a very large number of participants. There is another solution, however. I worked on this with Ari and Lenstra in 2017. We proposed the following protocol. It starts in the same way. Everyone generates their own random bit string RA, except this time, instead of broadcasting a commitment to their random bit string, they publish the bit string right away without trying to hide it. So that solves the 2 rounds problem. Now you don't have a second round, so you are never waiting around for people to open their commitment. Everyone has revealed their randomness right away, so you're not waiting for anyone to finish anything anymore. So it scales. The problem, of course, is that now the last person to reveal their own randomness has full control over the final random number. Suppose I'm participating and I know there are 1,000 participants and I see everyone's randomness and I'm the last one to decide. I can choose my randomness to be exactly what I need for the final number, the XOR of all the random numbers, to be whatever I want it to be. So it's totally insecure. So instead of taking the exclusive OR of all these random values, we propose to, well, concatenate them and then feed them to some function that takes time to evaluate, say 10 minutes. Then the final random number, which is this function that takes time to evaluate, evaluated at the concatenation of all the random values, will not be known until 10 minutes after the last random number is revealed. So the outcome, the random outcome of the protocol, is totally unknown until 10 minutes after the end of the execution of the protocol. And this way, no one can meaningfully cheat during the protocol because no one knows anything about the outcome until much later. So this function that takes time to evaluate, we propose a candidate called SLOTH, the slow timed hash function. And you can easily see that it has all the requirements of a verifiable delay function. We want something that is slow to evaluate, yet we want it to be easy to verify so that anyone who wants to check that the protocol was executed properly then can check the correctness of the output without redoing the whole computation that might take 10 minutes. So here's the first application of verifiable delay functions that are useful to generate random numbers. And this is very useful in decentralized settings where you need to reach consensus with a lot of people. And they are, this method is practical, for instance, in a proof of stake protocol where you have to choose random sets of validators, or well, they've proven useful in various ways for blockchain. So now that I hope I've convinced you that verifiable delay functions are useful, I'm going to say a few words about how you would try to design such a function. So you want it to be slow, and you want it to be slow in a very safe way. You want it to be slow even for someone who has a lot of parallel power. So you're going to want to do some computation that's highly iterative. You cannot do the next step until you've finished the previous step. So the first thing you might be thinking about is some iterated hashing, maybe using some secure hash algorithm. You take your input X, you hash it again and again and again, maybe 1,000,000 times or 1,000,000,000 times, depending on how long you want it to take. And the final Y that you get would be the output of your VDF. And indeed, if your hash function is secure enough, this would be highly sequential and pretty much impossible to parallelize. But how would you even check the correctness of the outcome? How would you check that Y is indeed X hashed 1,000,000,000 times without hashing X 1,000,000,000 times yourself? So there's no simple and efficient way to do this. There are some technical ways that would allow you asymptotically to check the correctness of Y faster using snarks, for instance, but not simple, not efficient enough. Instead of doing this, you could try to draw some inspiration from time lock puzzles, which are a different kind of cryptographic primitive introduced in '96 by Rivers, Chemira, and Wagner that also have this constraint of necessitating some computation that takes a long time to execute. And the setting they use to do so is a group of unknown order. So they take a group G whose order is not known by anyone. Think about an RSA group, for instance. You pick a product of two large primes, n equals p times q, and the multiplicative group of z mod nz, which we would call the RSA group, has an order that is unknown as long as you don't know the factorization of n. So you take such a group. And if you're given an element x in this group, you can compute x to the power 2 to the power t by performing t sequential squaring. So you take x, you square it again, you get x to the 4, you square it again, you get x to the 8, you do this t times, you get x to the 2 to the t. And as long as you don't know the order of the group or the order of the element x, you have no shortcut. You cannot compute your exponentiation faster than doing t sequential squarings. So the VDF could just be f of x equals x to the 2 to the t. So this is very similar to the hash-based construction I just presented, in that you just replaced the hashing by squaring. So it's not immediately obvious that you gain anything. And indeed, if I give you x to the 2 to the t and x, how do you check efficiently that it is correct? Well, there's no obvious way, but we can find protocols to prove the correctness of this claim. And this is the approach I took in 2019. It's also the approach that Christoph Pieczak took to design another VDF the same year, in fact, published the same week. So we would solve this problem through a proof of correct exponentiation. The problem we're trying to solve is we're given a pair xy, and some party Alice wants to prove that y is equal to x to the 2 to the t. She wants to prove this in a way that doesn't require the verifier to do a lot of computations. Because it's always easy to verify yourself that y is x to the 2 to the t by just redoing the computation yourself. There is no secret involved here. The only problem is that t will be huge and you don't want the verifiers to do this huge computation. So we're going to do so by allowing Alice, together with y, to publish a proof pi of correctness. This proof will be a proof of correct exponentiation, so that given the triple x, y, and pi, anyone can verify efficiently that y is indeed equal to x to the 2 to the t. I'm going to present to you the method for this protocol in an interactive way, where Alice is not trying to convince the rest of the world, but she's just trying to convince a verifier, Bob, whom she's talking to. So Bob is going to be able to send her challenges. It's going to be an interactive protocol between Alice and Bob. And then we can use classic methods, Piaget heuristics, to transform this interactive protocol into a non-interactive proof so that Alice can use this proof to convince anyone without interacting with them. So here's what the protocol looks like. It's fairly short, fairly simple. So we start with the input xy, and Alice claims that y is x to the 2 to the t. Bob starts by choosing a random large prime number L. Large here, think of L as 256 bits, say. So Bob chooses this random large prime L. It's a challenge, and he sends it to Alice. Now, Alice performs a Euclidean division of 2 to the t by this prime L. And she gets that 2 to the t is q times L plus r. Q is the quotient and r is the remainder. And she sends to Bob x to the power q. And that's her proof pi. Now, Bob can easily compute the remainder, 2 to the t modulo L. And he will accept Alice's proof if pi to the power L times x to the power r is equal to y. Now, it's easy to verify that if everyone is being honest here, then the proof accepts. Indeed, pi would be x to the q, pi to the L would be x to the QL. You multiply this by x to the R, and you get x to the QL plus R, which is precisely x to the 2 to the t, which is supposed to be y. So if everyone is honest, the proof accepts. Later on, I'm going to try to convince you that if Alice tries to cheat, Bob will detect it. So for the moment, here's the non-interactive version of it. You just replace Bob by a hash function. So your VDF would be like this. You are given an input x in the group. And first you compute x to the 2 to the t. This is the slow sequential part, is the actual delay part of the verifiable delay function. Then you're going to compute a proof using the protocol I just presented, replacing Bob with a hash function. So instead of having Bob generate a random prime, you take a hash2 prime function that takes all the parameters of the protocol and generates a random prime number L. And now you do the Euclidean division of 2 to the t by q, and you compute pi, which is x to the q. And the output of your VDF would be the pair y pi, where y is, well, the actual output of the VDF, and pi is the proof of correctness. So you get a short output on the two group elements. And the verification is very efficient because you just have to compute pi to the L times x to the R equals y. L and R are rather small, about 250 bits. So you can do the verification with only two small exponentiations in the group. So the verification is efficient. Now, it is indeed slow and sequential because of the first step. You have to compute y equals x to the 2 to the t. And you also have this computation there, pi equals x to the q, that at first glance seems like it might also require a lot of time, because q is the Euclidean division of 2 to the t by L. 2 to the t is t bits long, which could be huge, while L is not so large. So q is actually has about the same bit length as 2 to the t. So computing x to the q, it looks like it's going to take as much time as computing x to the 2 to the t, which was the very slow part of the VDF. In fact, you can be a little bit clever and with some tricks, figure out that you can compute the proof in a much shorter time. Here's how short. I put here some of the parameters of some of the properties of the VDF I just talked about. So the first line is not exactly a VDF, it's SLOTH. It's the slow timed hash function I talked about when I presented to you the protocol to generate random numbers. The second line is the protocol I just presented to you. So you can see that SLOTH is not exactly a VDF because of the third property, the verification time. So the verification time are given in terms of group operations, and you can see that verifying takes time big O of t, which is up to a constant, the same time as the evaluation time. So verifying is very slow. Luckily, the hidden constant in this big O is very small, so it would actually take a constant fraction of the time it takes to evaluate to verify. But otherwise, SLOTH has pretty good properties. The proof is small, the setup is efficient, the evaluation takes time precisely t, only the verification is slow. The protocol I just presented to you has the same proof size, the same setup complexity, but is much more efficient to verify. There is a verification time that doesn't even depend on the time parameter t, it takes constant time. The drawback, however, is this little overhead in the evaluation time, because you have to compute the proof. You have to compute this pi to the q, which seems difficult to compute. As I said, you can make it faster than the obvious time it seems to take, which would be as long as evaluating the VDF, but it still adds some overhead of t divided by log t. So the full evaluation of this VDF would require times t, which is the actual time log time, plus the overhead t divided by log t. Okay, now we have other candidate VDFs. I already mentioned Kitchak's candidate, which is based also on these squarings in groups of unknown order, has very similar properties. It has the advantage of having a smaller overhead in the evaluation. So evaluating takes time t, the sequential part, plus a little overhead of size this time square root of t, instead of t divided by log t. So the overhead is smaller. The drawback is that the proofs are much larger. Instead of constant size, they are of size log of t group elements. And the verification requires also more work, bigger of log t work. There is another candidate based on isogenies that was proposed a bit later the same year, which doesn't even compute a proof. So there is no proof, there is just the output of the VDF. And the evaluation takes time t with no overhead because you have no proof to compute. And the verification is still very efficient, constant time. The drawback is that the setup becomes much more complicated. It takes time linear in t to set up everything, which can be a problem. Okay, so back to the protocol I presented to you, the version of the VDF that corresponds to the second line on this table. I promised to you to talk about the security of this. Showing you this protocol, I hope I convinced you already that if everyone is honest, then it succeeds. Now, what if Alice is trying to cheat? Can Bob detect it? So let's suppose she is trying to cheat. She's trying to convince Bob that y is equal to x to the 2 to the t, but it's not actually the fact. So y is different from x to the 2 to the t. You can translate this through the quotient of these two quantities. You let w be y divided by x to the 2 to the t. And Alice being dishonest means that this is not 1. So w is not the neutral element in the group. And I claim the following. For Alice to successfully convince Bob during the execution of the protocol, she must be able to extract Lth roots of this element w with good probability. Given that L is unpredictable, she doesn't know L beforehand, so she doesn't know L at the moment that W is generated. So Alice will be able to generate Lth roots of W for many large primes L. The proof of this claim is fairly straightforward. During the execution of the protocol, Bob generates a random number L, and assuming that Alice successfully convinced Bob, it means she was able to compute an element pi that passes the acceptance condition, that is pi to the L times x to the R is equal to y. Now, if we let rho be this element pi divided by x to the q, we can do this little computation and see that rho to the power L is actually equal to W. So rho is an Lth root of W. So indeed, if Alice successfully convinced Bob, she was able to compute this element rho that is an Lth root of W. So why does that prove security? Is it actually hard to compute Lth roots of an element W? Well, the assumption that this is a difficult problem is called the adaptive root assumption. The adaptive root assumption is a computational assumption expressed in the form that, in the form of a game, and the assumption says the game is hard to win. The game is the following: you have a player whose role is to find an element W in the group, other than the neutral element, and publish it. And then the challenger generates a random prime number L, and the player has to find an Lth root of W. And if in a group, this game is hard, we say that the adaptive root assumption holds. So in what kind of group can we hope this adaptive root assumption to hold? Well, first of all, you would need a group of unknown order. In groups of unknown order, we know a few of them. All of them come from number theory, and the first I mentioned was the RSA group. But first, I want to say a few words on why exactly is it important for the group to be of unknown order. It's pretty easy, but I think it's worth going through it. Suppose you have an element W in the group other than the neutral element whose order is known. And I claim that then it's easy to win the adaptive root game. And therefore, in this group, where you know an element of known order, the adaptive root assumption does not hold. So indeed, suppose you have W and you know that it has order n. During the execution of the game, the challenger generates a random large prime number L, and you can easily compute the inverse of L modulo n. modulo the order of the group. I say it's easy to compute it because L is a random large prime, so with overwhelming probability, it will actually be invertible modulo n. Once you have k that is the inverse of L modulo n, well, w to the k is an Lth root of w. And you have won the adaptive root game. So it's a problem to work in a group that has elements of known order. Therefore, you need a group with no element of known order. In particular, you shouldn't know the order of the group. I already mentioned RSA groups. They are our first candidate for groups of unknown order. You pick two large primes, P and Q, take their product N, you call this the RSA modulus. And the RSA group is the multiplicative group of Z mod NZ. As long as you don't know the factorization of N, you don't know the order of this group. And in fact, the two problems are equivalent. Computing the order of the group is equivalent to factoring N. So we have pretty good confidence that it's a difficult problem. We still have an issue with this group, which is that, okay, we don't know its order, but we do know some elements of known order, namely the elements plus or minus 1. So 1 is just a neutral element. We know it's ordered, it's of order 1. That's normal. We can't avoid that. But we also have this other annoying element, minus 1. It has order 2. So we could win the adaptive root game by saying W equals minus 1 and then extracting the roots of minus 1 very easily. To avoid this, instead of working directly on the multiplicative group, we work on the quotient of this multiplicative group by plus or minus 1. Essentially, we just get rid of minus 1, so that the only element of known order that remains in this group is the neutral element. So you can do this. And then in this group, no one knows how to find efficiently an element of known order. So the adaptive root assumption seems to hold. There is one last little problem with these RSA groups, which is for our VDF to work, we need that no one in the world knows the order of the group. Not even the evaluator of the VDF, especially not the evaluator of the VDF, because knowing the order would give you a shortcut and a way to cheat to produce misleading proofs. So we need an integer n that is a product of two large primes, but whose factorization is not known by anyone in the world. So how do you generate such a number n? The first solution would just be to assume a trusted third party. You ask this trusted person to generate the number n, and you trust that they will never reveal the factorization to anyone. This is not a very satisfying solution. The second solution would be to just generate a random, very large number n, just an integer at random, except you pick it so large that with very good probability, it has two large prime factors. This works in theory, but you end up with very large numbers n that would be very impractical. It would be very inefficient. To be sure that your number n has two numbers of, say, 1,000 bits, n would be probably of something like 30,000 bits, way too big for practical purposes. A third solution, which is actually the preferred solution, is to build this product of two primes, n, using some multi-party computation. It's the approach that the Ethereum Foundation and Protocol Labs are taking, working with a company called Legero. What they are trying to do is generate 3072 bits modulus n with secret factorization, using some multi-party computation that is n-1 maliciously secure, and for about 1,000 participants. So what they want is a protocol, and what they're actually designing is a protocol that can handle around 1,000 participants, and that outputs an RSA modulus with the guarantee that if at least one of the participants is honest, then the resulting number has a secret factorization that no one can know. If you know anything about multi-party generation of RSA modulus, this is a pretty challenging problem. And 2 years ago, no one would have hoped for such parameters, 1,000 participants and n-1 maliciously secure. But in the last few years, in the last 2 years, actually, there was a lot of progress, and this now seems feasible, mostly thanks to the all the momentum around VDFs and generating parameters for VDFs. But you can get rid of this problem entirely and go for another kind of group of unknown order. Also provided by number theory, you have class groups. And class groups are very easy to generate, much easier than RSA groups. To get a class group, you just need to generate a random large prime number P. And you generate your prime, you get a class group. And the prime doesn't need to be secret for the class group to have unknown order. Generate a random prime, the class group will have a large order that no one is able to compute efficiently. And this class group would actually be the imaginary, the class group of the imaginary quadratic field of discriminant minus your prime. So I'm not going to go into the details of what class groups exactly are. All you need to know is that it's very easy to generate. Just generate a prime, you get a class group. And given the prime, computing the order is very hard. It has complexity L of 1/2 using the classic L notation if you know about it. In comparison, the complexity of factoring a number of about the same size would be L of 1/3. And L of 1/3 is less than L of 1/2. So computing these orders is seemingly harder than factoring. So we have pretty good confidence in the difficulty of this problem. The big advantage of this class group is that the setup is very easy. You don't need a multi-party generation of anything. You just generate random primes. They don't need to be secret. And you can even generate a new prime at every instance of your VDF. So you get some kind of long-term resistance. And you still need to be careful though, because these class groups, sometimes nasty things happen. And for instance, you always can compute efficiently the two torsion part of the class group. That is the elements of order 2. So it's always easy to find all the elements of order 2 in a class group. So you need to generate your parameters in a way that you're guaranteed that no such element exists. This is feasible, you just need to be a little bit careful. Still, the setup remains much simpler. Now, an open question remains. These groups, RSA groups and class groups, well, they have unknown order, sure, but that doesn't necessarily mean that the adaptive root assumption holds. Indeed, it's not known that the adaptive root assumption is equivalent to finding elements of known order. We just have an implication. Well, we have some confidence that it's probably a hard problem in general, in the sense that it is hard in the generic group model. It's been proved by Bonnet, Boons, and Fish. But secure in the generic group model is not really hardcore security. The question remains as to, is it still as hard as it looks in RSA groups and in class groups? Well, we don't know for sure. At least root extraction, without the adaptive part of it, is believed to be hard in these groups. But the full problems are not known to be hard. There are bounties out there if you can solve some of these problems for a total of $14,000 published by the Ethereum Foundation. So you can go to this link and look up the bounties and try to, well, solve some of these problems. For instance, if you can prove the hardness of the adaptive root assumption or the equivalence of the adaptive root assumption to factoring in the generic ring model, you could already get some bounty. So that there are some probably reachable problems in there. Now I'm going to say a few words about the problem of guaranteeing slowness in the real world. Everything I said so far works pretty neatly in theory, but once you're confronted to the real world, then you run into all kinds of trouble. Here's the assumption we're doing. We're making what we call a time lock assumption, which is of the following form. Computing x to the 2 to the t actually requires t sequential squarings. And the time to compute x to the 2 to the t is about t times the latency of doing one squaring in the group. This is an assumption. We don't know how to prove this. We are assuming that to compute t sequential squarings, you have no choice but computing them sequentially. So there's two problems here. First, well, we don't know that this is actually true. And second, we need to understand perfectly what this latency is so that we can have a good estimate of the real world time it would take to actually compute this. So what is that latency? What is the latency of squaring in the group? And most importantly, what is the gap between the speed at which a random user can go and the speed at which a very rich adversary can go? Can a very rich adversary perform this computation much faster than the random user? It is expected that someone very rich will be able to go a little bit faster simply by buying very fancy hardware. But how large is this gap? In protocols that use VDFs, it is mostly okay if an adversary can go a little bit faster, maybe twice as fast, maybe even 10 times faster. But the protocols break down as soon as the adversary can go 1,000 times faster. So you need to reduce this gap as much as you can, the gap between what a very rich person can do and what a random user can do. And well, it seems like a difficult problem, and the only obvious solution to this is to massively invest in building the fastest possible hardware for computing these squarings, and then make this hardware widely available. So this sounds like a very expensive and crazy solution, but it's actually what's happening right now, mostly thanks to the interest of the blockchain people in this technology. So there have been a few competitions to design the fastest possible methods to compute these squarings. So the Chia network organized a competition last year for the fastest possible software implementation of class group arithmetic, and mostly class group squaring, for a $100,000 prize. The VDF Alliance also organized a competition, this time for the fastest possible FPGA implementation of modular arithmetic, modulo 1000-bit RSA modulus, also for a $100,000 prize. And these are just the first steps. The next step would be the fastest ASIC design. We're expecting a significant boost in speed with ASIC. So another way to try and have some guarantees on the speed it will require to compute these sequential squarings would be to get some theoretical lower bounds. Going to prove bounds of the form, if I have a circuit that computes a squaring, then it must have depth at least something, at least some quantity. And the depth of the circuit will essentially be the time it takes to run the circuit. So we can prove theorems of this form. I worked on this with Ryan Williams this year, and we actually managed to prove something of the form, even computing the least significant bits of the squaring function. If you have a circuit that does that, it needs to have depth at least the log of the bit length of your input. We actually proved that a circuit that reliably performs squaring modulo n in binary representation has depth at least log of the bit length. So this is, well, it might be a first step, but it's not much really. It's very limited for several reasons. First of all, we assume binary representation of integers. So we assume a circuit that takes as input a binary representation of an integer and outputs the binary representation of its square modulo n. But it's unclear that binary representation is any good for modulo squaring. Maybe some other representation will allow much more efficient squaring. And in fact, what comes out of these competitions for fastest FPGA design for modulo squaring is that indeed binary representation is not the best you can get. But it's already a first step. The other limitation of this theorem is that it's only talking about doing one squaring. It says nothing about sequential squaring. And indeed, if I want to compute x to the 4, maybe I can do better than x squared squared. Maybe I can design a circuit that performs the computation of x to the 4 directly without squaring twice. So yeah, there's a lot of limitations, a lot of room for progress here. And that concludes my talk. It's everything I wanted to say. Now it's time for you to ask questions.
Thank you very much, Benjamin. It was a very interesting talk. And now other questions from the audience?
I have 4 questions, but someone else can go first if there is any.
You can start with your first question.
Yeah.
Actually, 2 of them are quite quick. Thank you very much for the talk, by the way. So this SLOTH function is just repeated hashing, is that correct?
The SLOTH function, no, it's repeated, the SLOTH function you're asking, right?
Yeah, SLOTH, yeah.
It's repeating repeated square roots. So to evaluate, you're given x, and you're asked to compute the square root of x, and then the square root of this, and the square root of this.
And this one does not have an efficient proof. That's the drawback, right?
It doesn't require a proof. Yes, the output is the proof, and you have semi-efficient verification in the sense that to verify that it's correct, you compute in the other direction, which is squaring instead of square root, and squaring is much faster than square root.
Okay, but it still takes t steps, but each step is faster.
Yes, yes. So in one direction you have t square roots, and the other direction you have t squarings. So you get some speed up, but not asymptotically as good as we wish.
Okay. And in this paper where they formalized the VDF, this Monash et al. Paper, does this have a concrete VDF construction, or is it just a formalization?
So they have a formalization and some candidates with issues. So they have a VDF that is I don't know. They don't have a construction that satisfies all the requirements they wanted. I don't remember exactly the limitations of them. Maybe a VDF that can be used only once, and then you have to throw away the parameters, things like this. I don't remember exactly. So they didn't have a full VDF candidate in that paper.
Shall I keep going? Is there anyone else with a question?
Sure.
Yeah, I had a question, in fact, about Bonus paper. I think from my memory, they had a construction based on like a finite field permutations.
Yeah, permutation polynomials.
Yeah. So what was
Yes.
wrong with that, if you can?
I don't remember. I remember they were looking for permutation polynomials with certain properties and couldn't find them. So there are known permutation polynomials out there that they could use, but had some problems. I don't remember exactly the limitations. I would have to look up the actual paper.
Okay, thank you.
Actually, I think that the gap between verification and computation is not T in that polynomial-based VDF. Is log T, something like that, I guess.
Oh, okay.
As I remember.
That's possible. I remember something like also, so the evaluation would take time T, assuming you have log T parallelism or something like this. So you needed some parallelism to reach the fastest possible execution. Maybe that was not the main limitation. I don't remember.
Okay, thank you anyway.
I have a question. So first of all, thanks for the talk. And as you said, the one of the big problems is that none of the existing VDF achieve the ideal sequentiality, namely still the fast processors can run the evaluation faster than others. So do you know of any iterative sequential functions that have better sequentiality and are suitable for constructing the VDF?
So you mean a VDF that would have some you would probably not be able to go faster by building some fancy hardware?
Yes, I mean maybe the gap between the poor processors and the fast processors smaller.
Yeah,
I don't know if
I don't know. No, I think that's tough because you can always build dedicated hardware that will go faster. So a way to avoid that in other contexts would have been to have functions that are very memory hungry or things like this. But I'm not sure this could be made to work very well for VDF. But maybe it can, but there is no known construction at the moment, at least.
Okay, thanks.
So the solution, as I said, has been to invest a lot of money in building the fastest possible ASIC and then make it widely available.
I see.
Yeah, for example, you might even do maybe going, if you compute instead of doing squarings, if you do fourth powers over and over again, and you have a circuit that computes the fourth power, if this one is faster than like doing twice doubling.
Yes, sure, but the competitions they are running for building the fastest methods for sequential squaring, it's not just for one squaring, it's actually for the sequence. So if they figure out that the fastest way is to compute the 8th power, then they're going to do that. And there are articles, actually, there are papers that propose to compute them by batch. So you compute I don't know, maybe to the power 8, to the power 16, and essentially can go as far as you want, and you will get a latency that's as short as you want, but an area that increases so fast that you cannot run your hardware anymore at some point. So if you're trying to compute to the power 250 just in one batch, you're going to need an area that's so large that then you get delays in your wires that mess up your computation, and software is going there. So yeah, it's part of their competitions, figuring out what's the best strategy for sequential squaring, not just for one squaring.
Yeah.
Yeah, you can continue, Mohammed, with your other 2 questions.
Yeah, does anyone else have a question? I have 2 more questions.
Not at the moment. I will ask my at the end, maybe.
Yeah, actually, one question is, so there is all this work that is being done to compute VDF, for example, or even in this like proof of sequential works. Do you know of any works that can really make use of this, all the efforts that is being done? Like, can this, like all the function computation that is being done, be used for kind of like a good purpose, or?
You mean having a VDF where the computation that takes time is actually a useful computation? Is that your question?
Yeah, something like that, yeah. So the computation that you do also helps in some other aspect. Not just the...
You mean unrelated, maybe curing cancer or something?
Yeah, something maybe.
Yeah. I don't know. I'm not sure you can actually do that with VDFs because you really want something that's unparallelizable, and most real-world problems are very parallelizable. If you see what I mean.
Yes.
I mean, if you're trying to compute optimal folding of some proteins, that's very parallelizable work. It's not going to be a delay function. And I don't know.
Okay.
Yeah.
Okay, my last question quickly. So for this adaptive root assumption, can this be easier for some group elements and harder for the others? Except for this like -1 and +1.
So in the adaptive root game, the first step of the game, you let the player choose the group element. So already at the start of the game, if there is an element easier than the other, the adversary will choose it.
Yeah.
See? So when you say that the adaptive root assumption holds, it means it holds for even the easiest element. Because if it exists and if it's easy to find, the adversary will use it. Therefore, it should be difficult for every element. It should be hard to find even one element for which extracting roots is easy.
Okay. So in the assumption, it basically says that even for any of the group elements,
Yes. So for instance, if you use the RSA group without quotienting out -1, a player that plays the game in this group at the first step will always choose -1.
Yeah.
Will choose -1 because it's not the neutral element, and he's guaranteed to win because he knows how to extract any root of -1.
Yeah. Okay.
Okay, are there more questions from other people?
I've got another question. So what is to your knowledge, the most efficient post-quantum secure VDF?
There is no actual post-quantum VDF. There's somewhat quantum resistant ones. So in a slide, I mentioned that on class groups, since you can change the prime P every time you execute the VDF, you get some quantum resistance. What do I mean by that? I mean that if you have a quantum computer, you can break all these VDFs because you can compute the order of the group. And if you know the order of the group, well, not only you have shortcuts to evaluate by reducing 2 to the t modulo the order of the group and then doing your small exponentiation instead of big one, you can also cheat in the proof protocol. By quantum resistant here, I mean that if you change P every time, you need the quantum computer every time you want to break one computation of the VDF. So instead of breaking the setup, you need to break every single execution. So you need your quantum computer sitting around every time you want to break a VDF. So that's the most quantum resistant we have so far. I'm hoping we can get better constructions. But there was a paper published this year, I think at Crypto, saying that if you're trying to build a VDF using groups, if you know the order of the group, then it's not going to work. So to build a VDF in a group, it's necessary that the group has an unknown order. In particular, that means that you're never going to get something quantum resistant if you're just based on group arithmetic.
But isn't this isogeny-based construction from this Luca De Feo et al?
No, so it's misleading because now everyone associates isogenies with quantum resistance, but you can also break their VDF with a discrete log computation.
Okay. Oh, I didn't know that.
That's interesting. More questions? If not, maybe one simple question from me. Yeah, in our group, we have researchers working on VDFs and VRFs, and we can see they have similar security properties, like the uniqueness. How would you say, are there similar VRF and VDF, or are they related somehow to each other? Because they have also similar applications, for instance, in the construction of randomness packets, or
yeah,
so completely different primitives.
Actually, I don't know much about VRFs, so I've never actually looked at this close enough to tell you how closely related they are.
Okay.
So I have no answer for you, sorry.
Okay, it's not a problem. Okay, I think that's all. Thank you very much. It was a really great presentation.
Thank you.
And I think
well, thanks again for inviting me to speak here, and thanks for all the great questions. It was a pleasure.
Yeah.
Thank you very much.
Thank you.
Bye-bye.
Thank you.
Bye.
Thank you.